Okay, so I believe we are now online. Hello, everybody. I hope you can see both of us and see the slide on the screen. Today is a great pleasure for our final IOP evening lecture, the final of the season, to keep the best for the last, actually. You know that we've got speaker from Bavaria. When I went to Bavaria, I was really shocked that they are eating the dessert at the beginning. They have something with marmalade, and before they eat the pasta or something like that. While our Mediterranean culture is that you keep the best for the last. So you have the dessert, the sweet thing at the end. And that's how we programmed our lectures, actually. We kept our very best lecture for the end. So that's the lecture for tonight. Professor Jonathan Finlay, who will tell us about the 2D materials and the third dimension. So to introduce very briefly our speaker, which is very difficult because he did so many things, I can say that he's actually a UK native. He's working in Germany, in Munich, the Technische Universität München, the TUM, but he's himself from Manchester. At least he got his physics degree there in Manchester. Then he did his PhD at the University of Sheffield in the group of Professor Maurice Kolnick. I think he was already called the LDSD there, the Low Dimensional Semiconductor System, something like this. And after getting the PhD, which was in '97, something like that, he went with a prestigious Royal Society fellowship to work at the TUM already in Munich, in the Walter Schottky Institute. And there already, it seems that it made, if you look his biography, it seems he made a very strong impression everywhere he went, because he then went through a series of oscillation. He came back as a research assistant in Sheffield, and he went back again to Munich at the Max Planck Institute, got again a position as director of the semiconductor group in the Walter Schottky Institute. So lots of different positions. And in 2013, he became the chair of semiconductor quantum system, which is, I believe, at the top of the top position of the top institution. So our lecture, as I said, is really gifted, as is testified, is shown, is demonstrated by a very strange award, but that says a lot. The Golden Chalk is the award you get when you give such lectures. It's given by the students, who we all know are very tough in every judgment they make. So for several years, maybe 3, 4, 5 years, I don't know, many years, he got the Golden Chalk as a testimony of his brilliancy in delivering talks for the students, for the wide public. I will not tell you the big list of other scientific prizes and awards he got, because that would bring us too much into what Professor Finlay told us. I'll just finish by saying that he's an expert of semiconductor and metallic physics. He's working on the quantum mechanics of this heterostructure, nanostructures that he's drawing there. So he will be able to tell us about the specificity, the peculiarities of physics in 2 dimensions. Professor Finlay, it's a great honor, great privilege to have you with us tonight. Please, the chair is yours for as much time as you will need.
So Fabrice, thank you so much for that very kind and far too kind introduction. Actually, I feel like, how can I follow that now? You've built me up to live up to a lot. I also started by reading my title yesterday when I was preparing my lecture, and I thought it sounded a little bit arrogant, teaching 2D materials about the 3rd dimension. They know all about the 3rd dimension. Actually, the question is, can we learn about how they interpret their environment? So this talk is, it sounded a little bit like a Harry Potter book, so I took this spooky font for the first slide, 2D materials in the 3rd dimension. And as we're going to see, I'm going to be talking about 2-dimensional semiconductors, which, besides having some remarkable fundamental physical properties and optical properties and quantum properties, they also have this beautiful characteristic that they sense their environment. So if you place them on one substrate, maybe the material is a semiconductor. If you place them on another substrate, maybe the material becomes a metal. So they're kind of the chameleons of the semiconductor physics world. So I can't start a talk about 2D materials without, I don't know if it's where it began. I mean, nature, it began millions of years ago, but the structure of graphite was here determined by John Desmond Bernal in 1924. He was a very famous Irish, I think, crystallographer who showed that graphite was a layered material consisting of thin layers of sp2 hybridized carbon. That means that the carbon atoms hybridize their orbitals to form these 3 bonds in the plane, and that these layers of carbon atoms are sticking together via relatively weak van der Waals interactions. Yeah, and I'm sure many of the people listening to this lecture will know what happened next. Well, basically in the early 2000s, Andrei Geim, Konstantin Novoselov and their groups, kind of, you hear different stories, but I like to believe the story that they did this on a Friday afternoon, seeing can you exfoliate materials. Actually, there were other people in the 1960s who also tried to mechanically exfoliate thin layers of materials, but what these guys did, which was amazing, is they really managed to get down to the monolayer limit where you have a single layer of carbon atoms. Now, this talk is not about graphene, but I think it's important to kind of, graphene is, if you like, it's the standard, the gold standard 2D material. And I hope there are no graphene protagonists listening, because I'm going to say that if you want to do optics and semiconductor physics, it's maybe not the most useful material. This is what it looks like. It consists of, as I mentioned, atomically thin sp2 hybridized layers of carbon atoms. And the reason it caused such a stir is not just because one can exfoliate a monolayer 2D material, which had been predicted to be unstable, but actually because it has this very remarkable band structure. So forget about the equations, unless you're a theorist, and take a look at this picture of the electronic band structure. There you see the filled orbitals at the bottom. These are the valence bands. There you see the empty orbitals at the top. This is the wave vector of the electron propagating in the plane of this graphene monolayer. And you see, just for Fabrice, I chose it in French, this picture, and you see that it has this linear dispersion relation. And this is one of the very, very interesting things, that the linear dispersion means that the electrons in graphene, they behave really like massless Dirac fermions. So you can really do a lot of very beautiful physics in graphene. So my message is graphene is a material with a very curious band structure, massless particles. Here, this has been euphorically confirmed by many experiments. I'm showing you here one of them. This is ARPES spectroscopy, showing measurements of the band structure. There you see the valence band just as it should be, sitting right on top of what you can calculate with tight binding theory yourself. And if you look at the vicinity of the Dirac point, that's this point right here, you see beautifully that essentially you have this linear dispersion relation. So I don't dispute, and I won't dispute, and I shouldn't dispute that graphene has many superlatives in terms of its quantum transport properties, things like record room temperature, the electron mobilities, a very interesting magnetotransport behavior, more recently magic angle physics, which means if you make a bilayer of these materials for one particular relative angle between the two layers, you get remarkable things like flat bands and superconductivity and strongly correlated physics. So there's a gold mine of beautiful physics in graphene materials. But for me, as a guy who does optics and has done optics for a long time, graphene's a bit of a letdown because it doesn't have a band gap. And that also means that it's difficult to make devices like transistors, semiconductor devices, where you want to use electric fields, metal gates to control the electron density. So in a way, you can shift the Fermi level around, you can change the electron density and the hole density, but you would like to have other materials. And that spurred actually also a long time ago people to look into the kind of wider family of two-dimensional materials. So there are many 2D materials which are predicted theoretically to occur and also actually isolated and observed now. So for example, graphene we've already looked at. If I go down the group 4, you would expect that if carbon does this magic trick of sp2 hybridization, you would expect silicon and germanium to do it as well. And 2D forms of silicon and germanium in the form of silicene and germanine both exist. There are wide bandgap materials. If I go either side of carbon and I make boron nitride, it has a similar lattice structure to graphene. but the two atoms are different. The bond is much, much more polar, and that turns this from a Dirac material into a very wide bandgap insulator, which is very, very flat and very often used. I'm going to tell you in a while to cover everything you've ever met with boron nitride to make the properties of these 2D materials better. There are other materials, I don't have time to talk about them, of course, but what I wanted to mention is all of these different 2D materials have kind of interesting properties. Graphene, silicene, germanium are all Dirac point materials. Boron nitride, I've told you, is an insulator, and black phosphorus turns out to be a rather difficult to handle semiconductor. Moving on, there are a whole family of materials which are known as the bit of a mouthful, the transition metal dichalcogonides, or TMDCs. These types of material typically take a transition metal together with a chalcogen. They look a little bit like graphene if you look from the top, but from the side they are consisting of 3 layers of atoms. And I'm going to talk mostly in my talk today about these types of materials and some of the interesting properties they have. But there are many, many others, 2D forms of nitrides, gallium nitride, all kinds of things like this, metal chalcogonides, which tend to be topological insulators or have interesting properties. There are metal oxides, too many to mention, and monochalcogonides, things like, let's say, gallium selenide, gallium telluride. So the picture I wanted to give you at the beginning of my talk is that there's an insanely large family of these materials, and if you look in this beautiful review from Andre Geim, you can find out that they have very many interesting electronic properties. So some of them are metals, some of them are semiconductors, some of them are wide bandgap insulators, we've seen that, some of them are even semi-metals, but they also have novel topological phases. So they can have magnetic ordering, they can also be wild metals or topological insulators. So there's lots of interesting condensed matter physics to see in these materials. And what I would like to focus on is a little bit more proximity. What happens when you place either 2 of these materials together, or you place a material on a special substrate. And that the important thing is that due to the fact that the electronic states in the 2D material interact with their environment, you can both use the environment to control the electronic properties, to tune them and play with them, and you can also turn on and off interactions between different materials, for example, by rotating the 2 layers relative to each other. So this is the kind of thing that I'm become interested in over the last couple of years. So how do you do this? How do you create such heterostructures? Well, this is again a nice review, and maybe for the students listening, don't worry about picking up these references as we go. At the end of my talk, I'll show you a picture with all the references on it, and you can screen grab, or you can take a photo of the screen and get, if you like, all of the relevant literature for this particular talk. So this is the kind of thing I'm talking about, heterostructures formed from different materials. And of course, the next question everybody's shouting at their screen is, hey, Mr. Finley, well, how does one do that? Unless you're working in this area where you know already. Well, this is in a way the reason why so many people have started working in this particular field. You can basically buy yourself a flake from many suppliers around the world with dubious quality, and you can, using the sticky tape method, exfoliate from the surface a few layers of a particular material and position it on a substrate that you like. And this is actually a picture of the apparatus that we have in our institute. So it's in a glove box, but you see it doesn't look very sophisticated. It's a microscope. It's a rotation stage where you can basically rotate the crystal before you peel off a few layers of the crystal. And it has this green arm here, which you can position in space. You can tilt it very precisely, and you can also heat it. And you can use this arm to come with a kind of polymer, which is like a little sticky glue, pick up a few layers of this crystal, and then you can move it somewhere else and position it and rotationally align it. So to give you an idea how this kind of thing works, there on the left-hand side, you see a flake of boron nitride. This is about 30 or 40 nanometers thick on the substrate, imaged with a microscope. You see it's about 100 microns in size. And what's been done in a second step is a monolayer of molybdenum disulfide. That's one of these semiconductors. has been peeled off and placed on the top of this material. And then you can take, for example, a second layer of boron nitride, and you can place it on the top to make a kind of sandwich where you fully encapsulate one layer between the other two. And this is an example of something which looks a little bit like this heterostructure you see over there. Now, you can not only, people have been very smart, and you can now, once you've made such a structure, you can stack either monolayers, as I show you here, or you can also put layers of different materials together. Some are insulators, some may be graphene, and look at the interactions between them. And after you've prepared such a structure, you can actually develop methods to measure the orientation of the different crystal components with very high precision. So people can use methods like nonlinear optics, where you use short laser pulses to make second harmonic generation. For one of these hexagonal crystals, they're very nonlinear, so they tend to exhibit, if you vary the polarization direction, second harmonic generation only along special directions. So you can figure out the crystalline structure orientation from such a picture. And it turns out if you change the frequency of the laser, you can measure all of these different materials by tuning the laser to different frequencies. So by doing this, people have done beautiful work, and this is a nice piece of work from Andreas Müller's group from Vienna, where you see that what they did is they placed a monolayer of this crystal on top of a kind of bendy piece of plastic. And by doing this, you can bend this material. And when you bend it, you see that this second harmonic generation signal changes. That's just because you changed locally the crystal structure and the symmetry when you deform this 2D material. So the picture I want to give you is that via this pick and place, relatively simple nanofabrication, you can place materials together, you can align them, you can, let's say, have them interacting or not by changing the twist angle between them. And by doing that, you can go in some nice directions. So let me just summarize what I've told you so far. So I've told you that you can take 3D crystals of these materials, which are van der Waals bonded. You can easily exfoliate a monolayer because using sticky tape methods. And this talk is more or less about what happens once you've got your monolayers. What do you do with them? Well, you can either do top-down nanofabrication, and you can pattern them to look for quantum confinement effects and things like this. Or you can go the other way, and you can stack them up to make heterostructures where you have the orbitals of the electrons in one atom interacting with the neighboring layer. And this is actually turns out to be a very fruitful way of doing things. So this is kind of the cartoon. By stacking up different materials, it's kind of like nano Lego, and you can kind of turn on interactions between different materials. And we all know in the middle of a pandemic, you guys in the UK are doing very well right now. We're not doing so well. So we know that interactions are everything. This is an example where interactions are really extremely important, and that's what we want to do in the kind of research that I'm going to be telling you about. So I think it's important to tell you a few fundamentals, and I'm going to focus, I can't talk about all of these different materials, so I'm going to focus on one of them. And this is one of the most commonly studied two-dimensional semiconductors, that is molybdenum disulfide. So this material, so these are transition metal dichalcogonides like molybdenum disulfide, where M would be a transition metal, X would be the chalcogen atom. They naturally come in two kinds of crystal habits, and I'm only showing you one of them here. That is the 2H stacked version of this crystal. So there you have, if you look at two adjacent monolayers of this material, you'll see that one of them is kind of flipped over compared to the other one. So that means that you have this interesting behavior, whereas with one layer it has inversion symmetry around the flipped vertical direction, but if you put two layers on there, then it has different symmetries, and this changes the properties of these materials really a lot. If there are any chemists listening, this is an Institute of Physics lecture, so probably there might not be, but who knows. This is showing you the electronic structure of these materials. It's not so important for today. I just wanted to show you a cartoon of a monolayer of these materials and to tell you something interesting which happens about the band structure as a function of the number of layers of these crystals. So to give you some numbers, the thickness of one layer of these crystals is about 0.6 nanometers, and the van der Waals gap between the middle of one layer and the middle of the other is about the same kind of number. It's a little bit more because, of course, there has to be some Coulomb interactions here to make the van der Waals bonds between the two layers. Now, that's the crystal structure. You can exfoliate single layers. The interesting thing is, of course, what happens to the band structure when you go from lots of layers, like let's say this one over here, four or five or maybe 10 layers, and you go down towards a single layer. So for the non-condensed matter physicists, this picture here is probably a confusing one. If you're a condensed matter physicist, you'll recognize this as the schematic band structure. That's the wave vector of the electrons. This is the energy of them, and you see that there's a band gap at this region here. But you'll notice that in the bulk material property, these materials are indirect gap semiconductors, just like silicon. So for people doing optics, this is generally not that interesting because basically optical recombination is not very efficient because crystal momentum is conserved. The light doesn't carry away any crystal momentum. So this electron here will not recombine efficiently with a hole. It needs a phonon for this to take place. So this is, I mean, it's known since the 50s or even beforehand, 1940s, what the band structure of this material looks like. And they were kind of ignored for quite a long time, or studied and then forgotten, and then studied again and then forgotten again. The interesting thing happens when you go from bulk down towards, say, 2 layers. So you didn't notice that. There's bulk. If I go down to 2 layers, you might see that this band here is kind of changing. So look at the gamma point. That's k equals 0. You see the valence band goes down a little bit when I go to 2 layers. And if you look here at the conduction band, you'll see that the conduction band doesn't do much, but here at other points in the band structure, the band minima kind of realign themselves. And the reason for this is that at the gamma point, the band structure is mostly built from hybridized pz orbitals of the, let's say, the chalcogen atoms in the crystal. So there are the chalcogen atoms on the outside. The pz orbitals kind of stick out from the surface, and that means if you place 2 layers together, of course, these orbitals, if you align the 2 crystals correctly, they interact with each other, and therefore you would expect a strong layer-to-layer interaction via these orbitals here. The interesting thing is if you go from 2 layers, there's 2 layers again, down to 1 layer, then for 1 layer, this interaction is completely switched off. There's no sparring partner for these crystals to interact with. And then the semiconductor undergoes a transition to a direct bandgap material, where actually, if you look at the gamma point, you see here, gamma point is going up, up, up. The K point, not much is happening. Let's go back and just look at that. K point, there's the K point, there and there. Not much is happening when you change the layer number, and therefore it becomes a direct bandgap semiconductor. And the reasons are fairly complicated, but they're actually related to the fact that at the K point, mostly the d orbitals are interacting, and essentially they are more ambivalent to this interlayer coupling than the p orbitals at this gamma point. So the bottom line is when you go from a bulk crystal to a monolayer, this becomes a direct bandgap material. Now this was noticed, a little over 10 years ago. So this is one of 2 very famous papers. The other one I'll show you in a second. I have to update this slide every time I give a talk because this is now cited 10,000 times, more than 10,000 times in a little over 10 years. And most of these citations have come in the last 3 or 4 years. But what it shows is photoluminescence arising from a monolayer of such a crystal. You see it's very, very bright. And also a bilayer of such a crystal where suddenly the luminescence just disappears. There you see a similar type of picture. So this is luminescence recorded with a more patient person, so over long integration times, looking what happens at the position of the luminescence from the band gap. And there you see a nice picture which shows an SEM image of an electron microscope image of one of these flakes. There is a monolayer region. These white dots here are holes. And you see that if you look at the photoluminescence coming from this flake, there's almost nothing coming from the bilayer region. That's here. Most of the luminescence comes from this monolayer thick region. This arrow here should go all the way to this part. And moreover, when you go on these holes here, the luminescence is much, much brighter than when you go on the substrate material. So this was really proof, if you like, that the luminescence, the semiconductor does undergo a transition from indirect to direct as you thin it down to the monolayer limit. And there was at the same time another very important publication, which is also cited about 10,000 times, observing essentially the same thing. And of course, this set people about going to all of these old materials to try to find out which of them really also have interesting properties when you go down to the monolayer. So I'd like to now talk about some of their interesting properties. The first interesting property is these materials have extremely tightly bound excitons. So the electron hole pairs, which are generated when you promote an electron to the conduction band, they interact via the Coulomb interaction, and it turns out that in monolayer materials, this Coulomb interaction is very weakly screened, so the exciton binding energy becomes very, very large. And let me just illustrate this for the non-experts. So here you see a kind of cartoon picture of an electron hole pair, and here you have to imagine that this electron hole pair is confined within one of the planes of the crystal. That's because essentially the interlayer coupling is relatively weak, so it doesn't move like in a 3D material in all 3 dimensions in space, but is mostly localized within one of these layers. And you see the electric field lines penetrate through the surrounding 2D materials. Here I have many layers of this crystal. So in that kind of situation, in a bulk material, you would have a relatively weak Coulomb interaction with a rather low exciton binding energy and a rather large exciton Bohr radius. And if you look at the optical properties, what you expect is an excitonic peak, which is relatively close to the edge of the free electron hole pair, or let's say interacting electron hole pair bandgap. If you now thin down, so here I'm showing you in my nice animation, which took my student a long time to do, thinning down from bulk to 5 layers, and then to 3 layers, and then eventually to 1 layer, what you see in the cartoon is that all of these field lines now are permeating the vacuum. So if you remember in the Coulomb interaction, the dielectric constant comes in the denominator, you'll see quite clearly here that here you'd expect a much lower epsilon than you would for the situation where you have a bulk crystal where epsilon would be much higher. So screening is very, very weak. And what this does is it creates an extremely large exciton binding energy. So to give you some numbers, the exciton binding energy of the lowest energy exciton below the onset of the optical absorption is between 3 and 700 millielectron volts, so nearly an electron volt and this is compared to typical semiconductors where the binding energy is a few millielectron volts, or maybe a few 10 millielectron volts. So this is game-changing in terms of the excitonic physics. So the physics is determined by excitons, the optical physics. So one has a strong Coulomb interaction, very large exciton binding energies. These excitons are particles which form very quickly. They don't care about their environment, and they're also rather small. That means their coherence volume is relatively small, and the interaction between the electron and the hole is also, despite their small size, it's actually quite strong. So the radiative lifetime can also be on the order of a few picoseconds compared with tens or hundreds of picoseconds for other types of semiconductors. So they're very optically active and very strong exciton binding energies. For the enthusiast, there's also interesting physics here in the screening, because in a 2D system, you don't have a regular Coulomb potential. You have something which looks more like a Keldysh potential or a Ritover-Keldysh potential. And there I showed you what's important is this dielectric constant, which pops up here in the denominator. That is very small in this case, which gives rise to strong electron Coulomb interactions, electron hole Coulomb interactions. Let me show you this by showing you for a bunch of different materials the excitonic luminescence spectrum. So you see here for 4 different types of TMD semiconductors, the luminescence, you have to trust me, but these peaks here, the highest energy peak, that is then the neutral exciton emission for these different materials. And these lower energy sharpened peak, they can arise essentially from the fact that you can have an excess of charge carriers, and particularly in naturally occurring crystals or lower quality crystals, the native defects in the material, so sulfur vacancies, for example, are enough to give you rather large background charge densities, and that can give rise to lots of 3-particle complexes called trions, which have a different binding energy. And I just want to draw attention to the difference in energy between these different 2-particle and 3-particle states. It's of the order here of about, what is that, about something like 30, 20, 30, 40 milli-electron volts. So it's an order of magnitude bigger than typical values you find in other semiconductors. So if you like, they're kind of excitonic physics like you have in other types of semiconductors, but taken to the extreme because of the very strong exciton binding energy. There's also a lot of beautiful physics going on in terms of looking at non-hydrogenic Rydberg excitons. We know from, if you've studied hydrogen atom, and all physics physicists have been tortured with the physics of the hydrogen atom, or tortured or fallen in love, depending on what your perspective is, then you'll know that the energy levels are determined by the spherical symmetric potential. That gives you a Rydberg series. Here we have a potential which is essentially in 2 dimensions with anisotropic screening, and that gives rise to a non-hydrogenic Rydberg series. So there you're seeing essentially reflectance spectroscopy, where you can pick out these different excitons, and you can pick out the 1, 2s, 3s, 4s, and 5s Rydberg states. So there are many Rydberg states with different diameters as you go to essentially larger principal quantum number. And this is then showing examples of experimental measurements which have been done. I've put the references here of the energy of these different excitons relative to the free particle band gap. And this is what you would expect to get essentially from a 2-dimensional Coulomb potential. And you see that it doesn't quite vary according to 2-particle to Coulomb potential. And that's because essentially the screening here is also very anisotropic. It's a very interesting problem, but I won't jump into it in great detail today, but you can ask me if you're interested in also discussing these things. So interesting asymmetric screening physics in these 2D materials. I would like to give you now a golden rule if you're an experimentalist. So if you've turned off or switched off, or you're doing something else, this is where if you're an experimentalist and you want to work with these materials, you should come back on board. There is a golden rule in this type of material physics, and that is encapsulate everything, the lab, the material, the student, everything should be encapsulated in boron nitride. And to illustrate why I say this rather flippant remark is shown here on the left-hand side. It's the same, actually not the same monolayer, but it's the same crystal, the same natural crystal. And if you exfoliate a monolayer onto silicon dioxide, that is high quality, device quality silicon dioxide, and then you look at the photoluminescence spectrum, it's very, very weak. The exciton is very, very non-pronounced, it's very weak, and you see mostly this trion peak, the negatively charged exciton, indicating this is heavily doped, and also this very, very broad background, which arises from defects within this material, which are not passivated and are trapping electrons. If you take the same kind of crystal and you, instead of putting it on silicon dioxide, but you put it on boron nitride, and you see the luminescence as you see here. Firstly, it's about 2 orders of magnitude brighter, so the quantum efficiency is much higher. You'll see that the line width here becomes extremely sharp, and therefore the quality of this material is much, much better. So this is why I say everything should be encapsulated in boron nitride. It improves the electronic and the optical quality a lot, and this is a trick which of course was learned from the graphene community. So when you do this, you see very, very bright and very stable luminescence. You see that the defect and adsorbate related luminescence. Here you see a free surface with dangling bonds from defects which can catch atoms. They give rise to this defect band, which is very broad. You prevent that adsorbate chemistry from happening. The photochemistry doesn't happen here. So the L peak is strongly suppressed. And also what I would like to stress, but is not apparent from this picture, is the line width here at room temperature becomes basically homogeneously broadened. If you measure the lifetime of the exciton and you measure then the line width, it turns out that the line width is basically given by homogeneous limit at low temperatures, I should say. So this is very nice if you want to look at coherent light matter interactions, say with microcavities or something like this, because the exciton coherence is very, very robust in these systems. Just to fill in then the references in case you're interested, these are the references for this material. This is from our work, but actually many other people did the same thing a couple of years ago and do the same thing. There's been a lot of beautiful work with time-resolved luminescence to kind of establish that the best samples in the world now are, by many groups, are almost relatively limited. It turns out we can look a bit more detail at this kind of physics. So if I show you, and I have to jump over this quick because there's something I really want to get to in my talk. If you do kind of a monolayer of molybdenum disulfide and you study it with scanning tunneling spectroscopy, so tunneling microscopy, and there you see such a monolayer of molybdenum disulfide. It's sitting on top of boron nitride, so the red is the molybdenum disulfide. It's sitting on a flake of boron nitride, which you can't see very well here. And what one does, one has essentially a contact underneath, so you can come with an STM tip and look at tunneling spectroscopy. If you do this for a sample which is sitting on silicon dioxide and it's contacted at the side with graphene, then you can measure the density of states by varying the tip voltage relative to the molybdenum disulfide. And you see nicely it's a semiconductor. It has a band gap. The size of the band gap's about 2.1 electron volts. And you also see the potential relative to the tip. And if you take the same flakes, just like I just showed you with the optics, and you do a measurement on boron nitride, the flake is contacted now, you see that the band gap is shifting in its energy, and moreover, the size of the band gap is also changing. And the experts in the audience will also notice the onset of conductance in the conduction band or the valence band also becomes much sharper when you come to the boron nitride compared to the silicon dioxide. Now, the shift of all of the band gap and the change of the sizes, that just arises because you have a different dielectric environment. Boron nitride has an average dielectric constant of the vacuum, and the boron nitride of 3.45. Here on silicon dioxide, the refractive index is much lower, so that changes the size of the single particle band gap. You see it's very different for the two materials on different substrates. And if you compare optical absorptance with the differential of these curves to look essentially at the critical points in the band structure, I hope you can see that on the boron nitride, you see one absorptance spectrum, on the silicon dioxide another, and also you can measure from this the position of the real single particle band gap. And you see the single particle band gap goes from something like 2.3 to 2.4 electron volts just by changing the substrate the same material is sitting on. We also, and you can take the details from this publication, if you slide these two curves together to overlap the valence bands, we've translated the red one, so the valence bands overlap here, and you can see then very, very clearly that the conduction band has essentially a very much smaller onset in terms of the voltage, and this means that the size of the gap is different, and also the number of in-gap states caused by defects and disorder is also very, very different when you go on silicon dioxide compared with boron nitride. So boron nitride reduces the tail states, it improves the optical quality, it kind of passivates some of the defects, and it also makes the system more intrinsic. I've shown you on the previous spectrum that the luminescence from the trions goes down, meaning there's less free carriers inside the material when you go to this boron nitride encapsulated system. So this is just a brief picture to show that the properties of these materials depend on the substrate they're sitting on. I would like now to move on to show you that we can actually, at the atomistic scale, change the properties of these materials either via top-down nanofabrication or by actually locally irradiating them with high-energy ions, in this case helium ions. So I'd like to show you a nice example of some work we've been doing together with Alex Vorleitner's group here in Munich, where we've been basically trying to create atom scale defects wherever we'd like to have them. Of course, this is a very futuristic picture, but we'd like to come very locally with a helium ion, focus it to a couple of nanometers in size, and try to create monotypical point defects which are optically active. And actually, it turns out this produces a trapping potential for electron hole pairs. It produces single quantum emitters site selectively inside this material. So I'll show you that we can use these things to generate site selectively bright and very sharp quantum emitters where you pre-program the positions. Now, this whole area, so if you're not an expert, quantum emitters in this context means a single center, so a single atomic site, which is capable of being excited, generating a photon, and then being re-excited. So you could imagine it as a two-level quantum system, a little bit like you study in quantum optics. It's something which was first noticed about 5 or 6 years ago. People noticed, like Rudi Bratzich's group from Münster, noticed that if you look at luminescence from these materials, there's the neutral exciton, and at low temperature and very low excitation powers, you see lots of sharp excitons. That's because wherever you focus your laser, there are different defects with different local energies, and that gives rise to these different sharp lines. And about a year later, there were published 4 papers back-to-back in Nature Nanotechnology, all essentially reporting similar phenomenologies. People have seen at room temperature in boron nitride, you can create or you can form defects, and this particular defect has very bright single photon emission even at room temperature. So these are some really interesting systems to look at. Why are they so interesting? I should maybe emphasize this now. If I go back to my picture before, they're interesting because you can place these materials on all kinds of other materials. Unlike, let's say, quantum dots where you have to site selectively grow them lattice match to another material with the similar lattice constant and similar crystal structure. Here you can just place a flake on the substrate and define an atomic defect inside it. So there are many ways which people have studied in the last 4 or 5 years to trap excitons in these types of materials. For example, you can take a flake and you can bend it, buckle it, and strain it. If you change the local symmetry, you change the band gap energy and you change the energy of the excitons. If you place the flake on top of a material substrate which has a dielectric modulation, let's say you have a region with a high dielectric constant, another region with a low dielectric constant at the interface, it turns out you get also localized excitons which are trapped, in this case, on a one-dimensional interacting channel. This is like dipolar excitons in one direction. It's a very interesting topic. Of course, as I'll show you, you can create point defects wherever you want to have them. This is an example of typical point defects in molybdenum disulfide. And a very, very vibrant research field at the moment is the study of heterostructures and bilayer heterostructures, where you can create moire superlattices by twisting the two materials relative to each other. And here you see a cartoon where there are 2 layers of TMDs on top of each other. And if I animate it, you can see as you twist them, you start to form regions where the atomic registry overlaps and other regions where they don't overlap. And this creates, if you like, a modulation in periodic in space and a kind of artificial crystal structure called a moire superlattice. And these modulations are very big. So in the conduction band, the energy wiggles as you move across the moire unit cell. It's about 12, it's tens of millielectron volts, much higher than KT, especially at low temperatures. So I want to show you 2 experiments. One experiment has been done by a number of groups, and this is actually the same experiment we reproduced in our own lab, and that is, for example, taking a substrate which is patterned in some way with some stressors, in this case by etching in a silicon dioxide substrate, some little posts, some nanoscale posts, placing a TMD material on top of this nanoscale posts, and where you have stress at the top of these posts, you change the band structure and create trapping potentials. This is work from Mette Atatürk's group in Cambridge, and this is from Brian Giraudot's group, and you see very nicely, it looks like something got stuck under the carpet. So here's a tungsten diselenide flake. Wherever you see one of these little pillars, you see there's a peak in the atomic force microscopy, and moreover, if you look at the light coming out, there's essentially localized and bright emission from these tips. That's where you locally create a minimum in the trapping potential, and by doing that, excitons tend to get trapped, and statistically they tend to end up here, so you get a higher luminescence yield from this region. We did very similar things, and it turns out these quantum emitters tend to be quite noisy. So there's where the neutral exciton should be. We've made one of these traps using strain. I did something bad there. with strain. And if you look at that, you see sharp line emission. The lifetime of these emissions are tens of nanoseconds, so much, much longer than what you expect for the free exciton, which is picosecond lifetimes. And if you measure the photon statistics coming from this emitter, that's done using a Hambury, Brown and Twist type experiment where you correlate subsequent emission events on two detectors. You see at 0 time delay, that's when two detectors click at the same time, you have a suppression of the counts, and that means you have a single photon emitter. So this is really a single localized trapping center for excitons. Now, we were very unhappy with this when we measured it 4 or 5 years ago, 6 years ago nearly. And the reason is this: if you look at, as a function of time, this emitter, you see that it's jiggling around all over the place. So essentially it's scattering, and this gives rise to a dynamical broadening. And this arises essentially because in the silicon dioxide substrate, you can trap charges, photogenerated charge. Excuse me, I just have to drink. And these charges, these charge traps can charge up and discharge again. And every time they do that, it causes a stark shift of the emission line. We and many other groups have tried to fix this by going to much cleaner substrates, for example, aluminum gallium arsenide, which has been grown in an MBE machine. This has much, much better properties, and there you see this jittering is completely gone when you do things correctly. Okay, so we were happy with this, but we were not super happy, and because of that, we tried to go a different way, and we tried to use helium ions and a helium ion microscope to locally create atom scale defects in these materials. So this is the rather brutal looking cartoon. We encapsulate a layer of molybdenum disulfide between boron nitride few layer materials, and we come with a helium ion very locally onto the surface. And why do we use helium ions? Well, helium ions compared to electrons, they're quite heavy, of course. They have much more momentum. And this picture here is showing you a stopping range of ions in matter simulation of the straggle of the helium ions as a function of the depth that you implant through boron nitride. So typically we're using in these experiments 10 or 20 nanometer capping regions of boron nitride. So this top layer is 10 or 20 nanometers thick. And then you see that the helium ions only interact with the material over a length scale of a few nanometers, about 5 or 6 nanometers inside the molybdenum disulfide. So you can locally, if you like, deposit energy and generate secondary electrons, which have a high kinetic energy. This is a 30 keV helium ion, and all of this energy gets dumped into secondary electrons in the vicinity of this focal volume. Few nanometer lateral resolution, and the question is, what does it do? Well, it does something interesting. If you take then this material, and this is the first experiment we did about 5 years ago, where we took the material and we basically bombarded it everywhere with a certain dose of helium ions. We did 10 to the 12 ions per square centimeter, thinking this would be, actually we started with 10 to the 14 and then realized this was orders of magnitude too big. And then we found out 10 to the 12 is also rather a large dose. If you then take this thing and you perform luminescence spectroscopy everywhere, you image the luminescence. So at every point on this picture, one optical spectrum has been taken. There you see some typical examples of this optical spectra. And you can see, in addition to the exciton peak, which is this high energy one, this broad band that I blamed on defects before, but you also start to see some sharp lines popping up in the irradiated region. And I have to just tell you, these lines don't pop up if you don't irradiate. You get the broad background, but you don't get these sharp lines. You can do statistics everywhere here. And wherever you see a sharp line, you make a histogram. And this is showing the relative energy relative to the neutral exciton of where these sharp lines pop up. And you can see that there's one particular defect, it's actually these ones here, which likes to pop up about 190, 200 millielectron volts below the neutral exciton. And that's one particular type of defect which is created with the helium ion. So just to show you some examples, if I go to this energy, then I can pick up discrete emitters at the orange points. If I move to this red energy, then I can pick up discrete emitters here. And if I move to this dark red energy, which you probably don't see any different to this, you see there are different. So this shows these are point-like emitters they're localized atom scale defects, and I'll prove this to you in a second. So wherever we irradiate, we see sharp line emission. Each peak is spatially localized, and the most frequently occurring peak, if I average all of these different spectra, I see exactly this peak, and that's the one which we saw in the statistics, which is the one that is generated by the helium ions. Now, these sharp lines are also discrete quantum emitters, and we can do that by looking at the luminescence as a function of time. You see the exhibit blinking, they go dark and then get bright and then go dark again. That only happens for single centers. If you had many, they wouldn't all go dark at the same time unless you were very unlucky. Some emitters at certain frequencies, they also exhibit some jittering, and this is showing random telegraph noise, meaning that you're seeing discrete jumps in the local electrostatic environment of this defect. And of course, if you look at photon statistics, you also see anti-bunching. That tells you you really are dealing with quantum emitters which are generating photons one at a time from these types of systems. Now that's nice. You might be asking yourself, okay, so Mr. Finney can generate defects by shooting helium ions at 2D materials. Why is it interesting? Well, it's interesting because one can do this site selectively. So here I'm showing you some data where we've basically irradiated only at certain positions with our helium ion beam, so a few nanometer size spots, and we've done it on the left here in this blue data on a sample which was already encapsulated with boron nitride, the green on both sides. So we've shot locally the helium ions in, created some atomic scale defects, looked at the luminescence, and what you see is that when you go down to the right dose, in this case about 2,000 ions over patch sizes of 200 nanometers, you see mostly the same type of defect. That's this defect that we just saw in the statistics, which pops up when the helium ions have been addressing the material. So between these spots, you don't see this sharp defect. If you do the opposite experiment, actually this is what we did chronologically first, where you bombard, and then after you've bombarded, you cover with the boron nitride. This is an example of one or two numerical simulations save you 6 months in the laboratory. But what we found out there is also quite interesting. We found out that bombarding creates then defects, and these defects are chemically active. So what you see is a much broader scatter of emission peaks around this defect, because the environment of one of these defects depends on what chemically binds to the surface. And of course, this is solution processing, so there's solvents, there's all kinds of things. Oxygen is actually the culprit, which is binding to sulfur vacancies in these materials. So you see, this is, if you like, quantum scale emitters, but they're also quantum scale emitters which look at their environment and go beyond their own personal environment, their own immediate environment. Okay, I'm looking at the clock, and I wanted just to ask, what is a civilized time for me to talk until, Fabrice? I don't know if you're able to just quickly tell me.
No, you've got time. You've got time.
Okay, great.
10 minutes.
Because this is probably interesting for you. So I want to finish with one last example, and of course, if you have questions, we can talk about many other examples. And the example I want to show you is of a heterostructure. And there's been, as I mentioned at the beginning of my talk, there's a lot of interest in artificial superlattices, Moiré excitons in these materials. And there's also a lot of interest in what happens when you stack two different materials on top of each other to form a heterostructure. Let's start with the heterostructures, and very widely studied. In fact, many combinations have been studied, but we and many other groups, for reasons of, let's say, convenience and optical quality, have made a lot of studies of molybdenum diselenide sitting on top of tungsten disulfide. And if you calculate using tight binding calculations, the single particle band structures of these materials, what you calculate is that the conduction band minimum of molybdenum diselenide, it lies below the conduction band minimum of tungsten diselenide, and the band gap is also smaller, such that the valence band maximum is in the tungsten diselenide and the conduction band minimum is in the molybdenum diselenide. Now, what happens if you excite with a laser an electron hole pair in these materials is you can tune the laser to the transition in one of the two materials. You create an electron hole pair selectively only in that material, and actually over extremely fast timescales, 100 femtoseconds, a little more, one of these two particles tunnels into the other layer, and you get something which is looking like this. So actually the hole is going over. This happens very, very quickly. And this happens, and what that does is it spatially separates them, and it creates an exciton which has a permanent dipole moment. This is just looking like a classical dipole. So along this interface, you imagine you have a series of excitons which have a dipole moment. And of course, we all know the dipole moment goes from the negative to the positive direction. It goes from up to down on this picture. So just to show you that this really happens, there is a cartoon of such a flake made in our labs, and there's actually on the left-hand side luminescence measurements. So it's this material. You see that where the two materials overlap, that's the green spectrum. It looks like this, and you see a very big peak at around 1.4 electron volts. And if I move my laser spot just onto the region where you have the tungsten diselenide, then you have essentially the exciton from the tungsten diselenide. And if you move it onto the molybdenum diselenide, the orange spot, you see the exciton from the molybdenum diselenide. So this peak here, this green one, this is this low energy transition. And actually, I won't show you data, but if you measure the lifetime of this, its lifetime can be tens or hundreds of nanoseconds because of this spatially indirect property. So it basically forms very quickly, it lives for a very long time, and each exciton interacts with every other exciton. And this is very interesting if you want to look at dipolar exciton gases and how they interact with each other. So just to summarize the properties, they have a longer lifetime, these interlayer excitons. So 10 to 100 nanoseconds compared with picoseconds. And they have rather a large static dipole moment, which means there's a repulsive interaction between them in these materials. So they have time to thermalize, to cool down, lower their kinetic energy, and then you can start to see correlation effects. If you're interested, people have studied the time over which this process takes place, and they form. This is from the group in Regensburg, Rupert Huber's group. There's other work on how these interlayer excitons thermalize. I'll show you all of these citations at the end of my talk. Let me just summarize by saying that they form very, very quickly. There's very fast transition of excitons into interlayer excitons without a free electron hole pair phase. They don't dissociate first and then form the interlayer excitons. They always are, let's say, two particle excitations which turn into other two particle excitations. And the thermalization dynamics is very interesting. It depends a lot on how you twist the two layers relative to each other. Because of that changes the way the two layers interact. So we again see that 2D materials, they're sensitive to what's next door and what the properties of those are. Maybe just to show you some other beautiful work, people have also seen the energy and the intensity of interlayer excitons depends a lot on the mutual twist angle. There you see work from Sasha Tartakovsky's group in Sheffield, where you see that as you change the angle, you change the energy of the exciton because they start to interact whenever the atom sites are sitting on top of each other. When you tune them so they don't overlap, they don't interact, and you even see anti-crossings in the excitonic spectrum from hybridization. And like I showed you at the beginning of my talk, you can use second harmonic generation and nonlinear optics to really measure the relative twist angle to a very, very high precision. So here you see measuring it with a fraction of a degree is not a problem. Deterministically making it with a fraction of a degree is not so easy. So this shows the interlayer excitons are very interesting. This shows that they have a dipole moment. If you put electric fields around them and you apply electric fields, just like a static dipole in an electric field, it should shift in a linear way. And they do indeed, as the voltage is changed, show very nice linear Stark shifts. You see very large Stark shifts, much, much larger than the line width. Moreover, there's a lot of beautiful, extremely interesting magneto-optical effects, which I don't have time to go into, but I could give a whole nother hour-long talk about this kind of stuff. What I want to show you in the last few minutes of my talk is I'd like to show you how we can actually trap one, then two, then three dipolar excitons in a strain-induced trapping potential, and you can kind of measure the interaction, the repulsive interaction between them. So for this, we've done the trick I showed you earlier in my talk, where we take essentially a pillar and we locally spike the monolayer, the bilayer here. So there you see the picture. If you have a good screen, or if we have enough bandwidth, you might just be able to see in the region where the two flakes overlap, darker spots. I'm just indicating them now. Those are these little pillars here. The pillars are only a few, they're about between 50 and 150 nanometers in diameter, but most of the strain-induced localization takes place at the corners. The first measurement I would like to show you is not measured on the pillar. It's actually where we place our laser beam next to the pillar on this flat region of the sample. And there what I'm showing you in this panel is the photoluminescence as a function. That's the energy of the light, frequency, and this is then the excitation power. And I just want to point out, we've measured here over something like 7 orders of magnitude in laser pumping power. So from fractions of a nanowatt all the way through to powers where we've certainly destroyed the sample locally. What you see in the luminescence is you see that the peak that's observed, the interlayer excitonic, kind of shifts to higher energy as you pump and pump harder, as you increase the density of interlayer excitons. So this is kind of the cartoon. This is now the intensity of this peak as a function of the pumping power. And this is the energy of this peak versus the pumping power. And you see at low pumping power, it doesn't move much for the first factor of 100. And that's the region where the density is so low that the excitons are not really repelling each other via the dipole-dipole repulsion. We also see in that range a linear power dependence, which is what you should expect for these non-interacting excitons. And if you pump more strongly, the power dependence turns into something which looks very much like a power law with an exponent of about 0.5. It's a bit less than 0.5. But basically for exciton and exciton annihilation, you would expect to see the square root of the power intensity dependence. So this, if you like, is evidence that we see a non-interacting regime. And when you pump strongly, you see an interacting regime where the shift, the blue shift also starts. The blue shift comes because the excitons repel each other. This is, if you like, lots of excitons. Now we move our laser onto the top of we move it from here onto the top of the pillar, and then we have trap-induced exciton trapping. So this is a typical data recorded. It doesn't look very nice, but I hope the student's not listening. It looks beautiful if he's listening. I'll show you some much nicer data on the next slide. Whereas if you measure on these different pillars here, you see that beyond the interlayer exciton, you also start to see lower energy features, just like I showed you with the helium ions and just like we saw with the pillars earlier on. And if you then take one of these things and you turn the laser power down by about 4 orders of magnitude, this is the kind of data that you see. So it turns out old people like me like this kind of format, young guns like this kind of format, because I like to look at spectra in this format. And what I want to show you is on the pillar, you see sharp line emission at low pumping powers. And I'll show you a zoomed in version in a minute, but essentially as you raise the pumping power, what we see is a bunch of lines sequentially appearing, and that's as you add dipolar excitons to this trap. So you start with 1, then you go to 2, then you go to 3, and these are all these features which are very, very small on this picture. I'll zoom in and show you. If you look on the Young Guns version of this, you can see nicely 1 dipolar exciton, 2 dipolar excitons, 3, 4, I don't know if you're kind I, 5 or 6, whatever, but you see a discrete change in the emission energy as you statistically load more and more dipolar excitons into this trap. Now what's going on here? Well, actually what's going on is classical physics in a way, which could be very interesting quantum physics. You have 2 dipoles, and you all know that if you have 2 dipoles, there's a dipolar repulsion between them, and that dipolar repulsion, it scales in a certain way. So in 3D, you know that it scales as a kind of inverse cubic kind of dependence, the potential between 2 dipoles. In 2D, it's a little bit more complicated, but nevertheless, you have a dipolar repulsion. So if you were to measure the difference in energy between the peak corresponding to, let's say, 1 interlayer exciton and the peak corresponding to 2 interlayer excitons, that would be a measure of the interaction between these 2 guys. If there was no interaction, those 2 peaks would come at the same frequency, of course. Yeah. So this, if you like, is a picture of how you expect, in theory, the dipolar interaction to vary. And what we do is we have a trap which forces these 2 excitons to stay in the same vicinity. They can't wander apart because they're trapped in some strain-driven trapping potential. So if you see, like my cartoon, which you might do, the trapping potential forces them together, and the dipole potential causes them to be repelled. And of course, the average separation between these two guys is the point where these two potential energies balance each other. So the trapping potential, if we have a harmonic trap, we don't know what the trap looks like, but it would look something like a harmonic trap going the other way. And therefore, the total potential would be the sum of these two dipolar repulsion and trapping potentials. It would look something like this, and it can entertain bound minima where you can trap a small number of particles. So the trapping potential stabilizes a few of these interlayer excitons, and it can stabilize 1 or 2 or 3. And the interesting thing is, if you have 3 dipoles, you can start to think about crystalline phases of those excitons which form. So I promised to show you the data from before in a bit larger scale. There you see it. There's the localized interlayer exciton, very low pumping powers. You only see 1 peak. If you pump a bit harder, you see this stuff here starts to become brighter. If you pump a bit harder, it becomes much brighter. And we can analyze the intensity dependence of all of these peaks, and it's actually a tour de force because the radiative efficiency is not very high because these excitons mostly decay non-radiatively. And what we find out is this one here varies linearly with the pumping power. That's what you expect for 1 exciton, just from Poisson statistics, throwing single excitons into a trap. If you look at these 2 peaks, they go essentially quadratically. So here it's been scaled a lot. That's the quadratic power law dependence on a log-log plot. That's linear. That's this dashed line. If you go to the higher order ones, if you're a kind reviewer, you can say it kind of looks a bit cubic, yeah. And the quartic ones goes even more strongly. So the point is, the higher lying features here, they start to become superlinear in their power dependence. And this is an evidence that what we're seeing are 1 dipolar exciton, 2, 3, these interacting states. And there I'm plotting the energy of all of these different states. So there's the monolayer, the single dipolar exciton. If you add a second dipolar exciton, we get 2 peaks forming. If you, well, within the error bars, we get 1 peak forming. But actually, there are 2 peaks there if you fit the line shape and look at it very carefully. And this energy here, this is the dipolar repulsion between 2 excitons separated by some distance inside the trap. Depends on the trapping potential, which I'll come to in a second. So what we can do is we can basically, for 2 excitons, we add a third one, it moves a bit more up. The fourth one, it moves a bit more up. This is this blue shift I showed you a couple of minutes ago. And if you measure all of these energy gaps, and then you can convert these energy gaps into dipole-dipole repulsions, and what we've done is something I'm almost ashamed to tell you. We've basically placed dipoles within a trapping potential. We've fixed the characteristic energy of the trapping potential and calculated the lowest energy configuration of 2 excitons or 3, or if you put 4 on, you can imagine there are different symmetries depending on where the dipolar excitons go as they avoid each other. And we've calculated the ratio between these energy splittings. And the classical or semi-classical model would tell you that the ratio of delta 1,3 to delta 1,2 should be about 1.3, and the ratio of delta 1,4 to delta 1,2 should be about 2. Yeah. Experimentally, we see actually remarkable agreement with these things, despite the horrific simplicity of our model. So we see a ratio of about 2 for delta 1,4. For delta 1,3, we see about 1.4. Within the error bar, it's exactly what we would calculate. And that allows us to vary the characteristic trapping potential and try to get an idea how far apart the excitons are. So that was the classical part. We've actually done this in a slightly more sophisticated way. So this is for different characteristic trapping potential length scales, going from strongly large characteristic energies in the parabolic confinement potential to weaker ones. And we can calculate then that the average separation of 2 excitons in the trap will of course change depending on the characteristic energy. So we can use this to estimate, because we know the dipole moment, so we can use this to estimate how far apart the excitons really must be in order to produce the splittings that we see. That's the last thing I'm going to show you. So there are the calculations. These are now actually quantum mechanical calculations, including different screening in the environment. These are effective screening constants. what you see there are essentially the splitting between the exciton and the biexciton. These interlayer excitons, as the confinement length scale goes up, the splitting goes down because the excitons move further apart and the dipolar repulsion is less. We then calculated also the exchange interactions between the fact that these, I didn't tell you, but these excitons also have a spin and they have a Valley index, and therefore the allowed two particle complexes depend on the fact that they must obey fermionic statistics. When you do that and you calculate, you expect to get a doublet, and I didn't emphasize it much, but we see a doublet for this bilayer system. From the doublet splitting, we can calculate the exchange energy splitting, and it turns out there's only one point in our curve, magically of course, where these two curves, the exchange splitting and the binding energy, where they both overlap. So this would tell us our splitting is of the order of, let's say, a confinement length scale of 3 nanometers. So it's of the order of a fraction of the Bohr radius of these interlayer excitons. And this is actually quite a nice result. Let me just say, going towards excitonic gases of dipolar excitons, which are cool, is what we're doing right now. It turns out 1 or 2 just to measure the interactions is nice, but what you'd like to do is let them cool and let the interactions basically fix the phase and start to look for coherent effects. Last slide, where is all of this going? Where are we and other groups going? There's been some remarkable achievements in the past 12 months, and a couple of the achievements are shown here on this slide. I won't discuss the results, but I want to just tell you, in HOMO bilayers, where you have tungsten diselenide on both of these layers, the twist angle here, just like graphene, gives rise to Moiré physics, and it gives rise to flat band physics. And one of these beautiful flat band physics effects is crystallization, if you like, the Wigner crystallization of electrons into ordered configurations. And this has been measured here in this work by Emma Regan, where you can see it's very small here, but this is the filling factor, this is the conductivity. You see at fractional filling factors of this level, you see conductivity anomalies. And if you look there and you look also, say, at the capacitance of these devices or the resistance, you also see anomalies. And this is evidence that these types of phases are being generated. So actually superconductivity and strongly correlated phenomena, not just for electrons, but also for dipolar excitons, are something which is certainly coming in the next time. I think it's going to be a very interesting few years with these materials. So with that, I should stop. Otherwise, well, the good thing about online is you can just quit and leave, yeah? But I mean, I hope you didn't, and I hope you enjoyed listening to some of the things we've been doing. I want to thank the people who are doing this together with us. There's lots and lots of people in Munich, too many to mention all by name. Theorists who we're very, very happy to collaborate with from Bremen, from Munich as well, and also we're collaborating with Brian Girardot's group and group of Ignacio Sirac. So I'm just very happy that all these people are so collaborative. And I want to fish for postdocs and PhD positions. We might have no vaccines in Munich, but we have probably the best beer in Europe. So if you want to do a PhD or a postdoc, then please send me an email. I'd love to hear from you. If you hate your PhD and would like to quit and come to Munich, you can also do this as well. Yeah. So with that, I say thanks for your attention. Thanks.
Thanks a lot, John. It was fantastic talk. It was very nice to go really at the edge of the state of the art with you. It's very nice to see and to learn from the experts in the field. So now for the audience, there is the time for questions. So you cannot ask yourself, you cannot speak your question, but you can write it down. So there should be a little box somewhere where you can type your question, and then I will read it to the speaker. And don't be impressed by the level of technicality. You can ask a very technical question if you're an expert in the field, or if you are much more pedestrian and physicist and came for the curiosity of the thing, you can ask much more broader question. Yeah, that's the good point of having experts in something, is that they can tackle all the possible questions. We already have one from Camilo Lopez. He asks, so I'm reading. In the figure where you showed us the energy line associated to various trapped excitons, why are the lines splitting into 2 and not into as many excitons are trapped?
So I think the question, if I'm correct, if I interpret correct, is pertaining to the last topic I showed you.
Yeah.
So it's basically this data. Maybe the questioner can actually confirm that, but assuming that's the case, of course, the number of lines which it splits into depends, of course, on the interactions, the exchange symmetries, and of course what the eigenstates are, what the degeneracies are between eigenstates with different spin and valley configurations. So for the bi-exciton, for 2 dipolar excitons, you should get 2 lines. However, for the higher order excitons, of course, you should get many more. The problem a little bit is in our data, at least at this time, our data was not well enough resolved. I didn't bring it with me, but I can show you more recent data where we now have much better line widths because we encapsulate these materials using boron nitride. And if you do that, of course, then you can start to resolve some of these fine structures. So it's a very good question, and the answer is they do theoretically split into more than just doublets.
Okay, we have a question from Miroslav Kolibal. He asks, thanks for the talk. Do you see any way how to avoid tedious procedures of bilayer alignment and grow these structures by any scalable technology?
It's an awesome question. It's also a question I've spent a good fraction of the past 2 years justifying to the German Science Foundation. And luckily they agreed to buy us a molecular beam epitaxy machine to really grow these materials. So my answer is, to do really, say, quantum physics, if you want to do quantum many body physics, of course, you can't live with a system which is heavily defected or is very, very, let's say, inhomogeneous potential landscapes. You would like to have the potential which you impose, whether it's a periodic potential or a linear periodic, whatever, you'd like to have that as the dominant contribution so that you don't get localization. For that, I'm sure that you need epitaxial growth of these materials. Let me give you one example. I indicated in my talk that you can put a flake across a material where you have 2 different dielectrics with different dielectric constants. If you do that, of course, and you twist the flake relative to this linear interface, then of course there's some kind of periodic potential along the one-dimensional interface. And that's very interesting physics. 1D dipolar excitons in a 1D periodic potential. It's something which you cannot study using cold atoms in an optical lattice, for example, because you can't easily make one-dimensional lattices. However, to get the nice physics out of that, and there's a lot of predicted nice physics, you need to have the periodic potential dominates over disorder potentials. And I think for that, epitaxial growth is going to be important. And we are just starting at the very beginning of growing epitaxially these materials now. There's a long way to go, but I think it will be like with 3-5 semiconductors. There'll be game-changing advances. You know, look back at the developments from quantum Hall physics to fractional quantum Hall physics. It was all driven by enhancements in the quality of materials. And I think it will be the same here.
Okay, thank you. So, ask your question. We've been warned by the IOP technician that helps us organize that it can stops abruptly. If you stop asking question, it will just terminate. So don't be shy in asking questions.
It will just kick us out.
Maybe in the wake of this question as well. So you showed us the big improvements that this brings, this new material, this new technology, the very strong interactions, the tunability, all this stuff. Are there any bad counterpart, some problems that the older materials were not facing, were not having?
Yes, there's lots. I mean, there are some specific problems which I'll come to in a second, but one of the very big problems is that the entire world is doing this right now. And the problem is that everybody has different samples because they're prepared from different crystals. They're prepared under different conditions. Some are cleaner than others. And that means there's a huge output of literature, and a lot of it is very misleading. So one has to be, as a student or a scientist in this field, extremely careful what you read, because you cannot read all the literature pertaining to these materials. It's just too much coming. If I come to more specific questions now, a lot of these crystals have been grown, for example, with chemical vapor deposition. And you can show thermodynamically that at the typical growth temperatures, there's a large density of chalcogen vacancies in these crystals. So it means that, you know, just because of the growth conditions and the temperature of the growth that you do it at, and the formation energy of the vacancies, you form lots of vacancies. So what will be very important is also methods to understand and to passivate these vacancies, either by terminating them with chalcogen atoms, taking the oxygen out. And people are doing thermal annealing treatments in, say, sulfur vapor atmospheres, and have shown that you can improve the quality of these materials a lot. And I think it's again back to a materials physics question. I'm sure that a lot of these, let's say, group to group and sample to sample fluctuations will be gone in a few years.
Okay. So if there are no more questions, you still have last chance to ask. Don't be shy. Speaker is very happy to answer all the questions you have. I will maybe ask last one. Again, ask while I ask. What would you say is the immediate applications? Is this for quantum physics or maybe classical devices, optoelectronics? What would be the big change in our life thanks from this emerging technology?
I mean, the nearest term applications will be transistors with very rapid switching behavior with voltage and things like this, and they have already been demonstrated with amazing properties. Of course, these things are not yet silicon, so integration is going to be very important. How you, let's say, if you want to make devices scale to make many of them. But I have to say, I personally am mostly interested in quantum many body physics in these materials. Yeah, so I won't be making transistors and I won't be making LEDs and things like this. I'm mostly interested in how one can use these materials to study strong interactions and strongly interacting many body systems. And I think there's at least theoretically, there's been amazing things which have been predicted. The question is, can the experimentalists and the materials physicists get materials good enough to study them?
Okay, so maybe superconductor, right? So we might have the next Nobel Prize giving the talk first at the IOP. So I see no more questions. Thanks a lot, Jones. It was fantastic to hear again from the best expert in the world about these very exciting topics. I'm sure our students who attended were really very impressed to see all this physics we try to teach them and see like this so brilliantly illustrated, and as well the experts, because I can see that from the questions that have been asked that we got some people who are themselves studying this field. So thanks again, Jones. It was very nice to close this IOP series with you. We'll see everybody next year for the next series, and if you want to ask questions, you can certainly contact us by email and we'll echo that to the speaker. So with this, I'll close myself, and then if you want to say goodbye, that's it. And that's the promised list of references. So have a good look at that. And the talk should be on YouTube, available at some point, right? So if you want to have the pleasure to see it again, it'll certainly be somewhere. So thanks, John.
I'll tell my son, he'll be very impressed that I have my own YouTube channel. Okay, take care. Good to speak to everybody, and take care and see you later.
Ciao, ciao, everybody.
Bye-bye.